I'd like to welcome you to the Saddlebrook Science Cafe series. I see a few more folks trickling in. Let me introduce myself. I'm Erin Dealey. I'm the Director of Recruitment and Engagement in the College of Science. Shout out for science. Woohoo! As always, we're delighted to return for our series From the Earth's Core to the Clouds. And just as a reminder, this is the third in our series for the fall semester. We'll have 3 more presentations in the spring, all tied to this theme. And before I introduce our guest speaker tonight, I'll just make a few announcements. First of all, welcome back to all of you that have attended this series, as well as series in the previously. I'll mention too, we're a little off on our date, and I just got word from a couple residents that there's Christmas party happening tonight. So I know it's a busy time of year. We're delighted that we have the crowd that we do, and thank you for making the time to come out. Just as a reminder as well, on our U of A Science Cafe website, which is included, the link is included in our brochure, which is on the table along with other brochures from the College of Science. So be sure to check that out. We have the link to the YouTube videos, which actually you can watch the video right on our website as well for all the talks, as well as tonight's talk and in the future. So sometimes you're traveling, and if you want to queue it up on your phone or iPad or something, you can do that. It's simulcast, so it happens in the moment, and then we cache it so you can watch it at your leisure as well. I just want to announce too that this is one in a series of 4 venues where we offer this to the community. Of course, this is the farthest north from the U of A campus, but we're also at Magpie's Gourmet Pizza on 4th Avenue. And then how many are familiar with Tumamoc Hill next to A Mountain? Excellent. Any walkers in the crowd ever do that? I'm really excited to announce we just formed a partnership with Arizona Sonora Desert Museum. And because that, is so reflective of Sonoran desert habitat and ecology, they're going to be coming to Tumamoc Hill at the base of that walking path, basically, which is paved road all the way to the top, with live animal encounters for the public coming up to speak. So the first one, I just got wind today, is going to be from 7 a.m. to 9 a.m. this Thursday, December 7th. I can't tell you what critters they're going to have, but they'll rotate 3 different animals through. And on our website, we'll also post the dates for January, February, and March. So they'll do this once a month for obvious reasons, but it's obviously free and just a way to interact more and learn more about the Sonora Desert ecology at Tumamoc Hill. And then our other venue is Borderlands Brewing. Anybody been to Borderlands Brewing downtown? It's a great community brewery. They host a lot of community organizations, and that is actually where our PhD candidates, who also have a great interest in bringing their research to the community and learning to give public talks. So we showcase them there, and they all are Carson scholars named for Rachel Carson. So they're typically interdisciplinary studies with an emphasis on sustainability. So of course, they're all listed in your brochure. We do recognize that this is the last for this fall series in the brochure. We don't have the updated brochure for spring, but Samantha and I will be working on updating our website for those spring talks to be listed by the end of this month. And then we'll have those brochures available in January for everyone. And do know that you can also check the other venues on the website. So this is a great time to say, could everybody turn off their cell phones or silence them? That would be great, just so it's not distracting while we're talking during the evening. I'd also like to say thank you to the DesertView Performing Arts staff for welcoming the College of Science in as part of the Science Cafe series. And just a reminder, this is a pure community partnership, so no money exchange. This is just out of the goodness of everybody's heart, so we hope you enjoy it. And we're really excited, in addition to bringing faculty from geosciences, the geosciences department supports this, and there's information out on the table too about that department if for any reason you want to support their efforts or learn more about them. So please pick one of those up. I'll also mention we have evaluations, and we really appreciate the feedback that you give to us from those evaluations. We share it with our speakers, which help them improve and enhance how they bring their science to the community. Also, you'll notice at the bottom of that evaluation form is a field where you can tell us about your interests, and we'll do our best to tailor talks for Science Cafe series based on your interest in the current research that's happening at the U of A. So you can also put in your email address, and I would beg of you to make it very legible so that we can put it into our database. We never ask for money or send you offers for things. We simply will send announcements about upcoming talks like this or events that you may be interested in. I saw several folks picking up our brochure about the Community Science Scholars Program. This just began this last fall. It's a great initiative. It's about 80% tuition reduction on current courses that community members can audit. So on the back are the listing of the classes that are available for spring 2018. And I will mention these are on-campus, in-class courses. So there's also a link on here if you want more information, or of course you can contact us in our office. But this is a wonderful new initiative for those lifelong learners if they want to gain from our amazing faculty that are great teachers. Maybe by a show of hands, how many of you have made it to Tucson Festival of Books, and even more so, right into Science City? We're going to start telling you about Science City. We see about 30,000 folks. We're about 1/3 the footprint of Tucson Festival of Books, and we're now the 3rd largest festival in the country. And the nice thing about science, and of course this is nonprofit, and over $1.5 million have gone back into our community for literacy efforts, nonprofit efforts, but we're the only STEM literacy in a festival of books in the country, which is awesome, right? We have such a great resource. So I just want to mention we do have the brochure that lists the dates and also the link to our website. So in addition to those 90+ interactive table activities and specific tents that are themed, we also have, how many of you been to the Mirror Lab? Right, those tours are free and open to the public all day, both days, as well as Flandreau Science Center. And then we have 9 open houses that day. And then probably most prominent is our main stage in the Science City tent. We have full panels of science authors, local and national authors. So you can check out that schedule as well. So I encourage you to take that. And it is for all ages. We also have our Science Cafe tent, where we have interdisciplinary research being shared by researchers at the U of A on specific topics. So you can check that schedule out and join us in a similar format as today. So just as a reminder, we'll have our speaker come up, give a presentation, then Samantha and I will roam the audience with microphones, and we'll do a Q&A for a period of time. And I will ask that when we hand you the microphone, please pose your question and hand the microphone back so that multiple people can ask questions. It's not just a dialogue with one person, right? And if for any reason, we'll just ask our speaker to repeat the question if it's not clear what the question was. And if we have enough time at the end, if you have a burning question you'd just like to direct to our speaker, she'll have a few moments after the presentation to meet one-on-one with folks. All right, without further ado, let me go ahead and introduce our speaker, Jessica Tierney. She's Associate Professor of Geosciences and Global Change. Her background, she received her bachelor's, master's, and PhD degrees at Brown University, and her postdoctoral fellow at Columbia University. She was a research scientist at Woods Hole Oceanographic Institute for 3 years after that. And the type of research that she's involved in is she studies how climate has changed in the geological past to inform where we are headed in the future. And she's been with the U of A faculty for 2.5 years. And tonight she's going to discuss how climate has evolved over geologic time, and we can use the lessons of the past to prepare for future climate change. Without further ado, Jessica Tierney.
All right. Thank you very much. Can you hear me? All right. Whoa. Okay, that's a little loud. That's all right. So, for those of you who've been waiting here for a while, you've probably been staring at this sort of trippy-looking simulation here for a number of minutes. What we're looking at here is actually CO2 emissions. So this is a high-resolution model simulation of CO2 emissions through the annual cycle, so 1 year. And if you've been looking at it for a while, you'll notice that during a certain part of the simulation, the northern hemisphere gets a bright red, so that means more CO2 is coming out. And then it sort of goes away for a while, and actually you see the tropical areas in the southern hemisphere is kind of taking over. And what that's reflecting is just actually the spring and summertime in the northern hemisphere, the plants are growing and they're taking up more CO2. And the CO2 emissions are concentrated in the tropics and then the southern hemisphere. And then the whole thing cycles again. And some other things that you'll notice is the source of the emissions, which is coming for the most part from North America, Europe, and China, with some contributions and sometimes in the year from the tropics and in particular Africa. So the reason I'm showing this is it's sort of, I think it's beautiful, but it's kind of scary as well, because it sort of represents how, as a species, we're intimately tied now to the Earth's climate system. What we're doing is getting into the atmosphere, it's getting into the ocean. We are now a part of the climate system. So indeed, we've now begun this trajectory. We've stepped onto the long road towards a future of higher CO2 on planet Earth. And it's a slow journey, right? This has already been going on for quite some time. We've been watching it happen very carefully since about the 1960s, when we first started to directly observe CO2 in the atmosphere by taking measurements on top of Mauna Loa volcano. So here you're seeing a climate scientist on the top of that volcano. This is a volcano on the big island of Hawaii, and he's setting up an instrument to actually measure the CO2 concentration in the atmosphere. And this has been going on since the 1960s. And these measurements have revealed that since that time, the concentration in CO2 has increased by about 100 ppm. So it started out around 320 and we're now about 410, so almost 100 ppm during the time that we have been directly monitoring the concentration of CO2 in the atmosphere. Now, to give us some more perspective on this rise, which we can directly measure since the 60s, we can actually get some help from ice cores, believe it or not. They're taken from Antarctica. And so ice cores, these are long cores of ice that scientists are drilling from the ice sheet in Antarctica with a lot of effort. Bringing them back up are really unique because they actually trap ancient atmosphere inside the ice. Pretty incredible. So when ice in Antarctica forms, at first it's snow, and there's air in that snow, as you might know. It's nice and puffy, but over time that snow compresses into eventually forming the hard ice. And during that process, which takes place over the top 50 meters or so of ice, there's air exchange, but once the ice is sealed in, that's it. And so then those bubbles in that ice, they reflect an ancient atmosphere. They actually reflect the concentration of CO2 at the time that they got sealed, right? So this is really excellent for us because we can actually go in and scientists, go take a needle, get that little bubble of air and analyze it in the lab and reconstruct what greenhouse gas levels were back farther in history than we can get from our observations on the volcano. And so over the past 15 years, 20 years, there's been a huge effort to do that. And now if we take the measurements from the ice and we put them next to the measurements from Mauna Loa volcano, so over here this is the volcano measurements, and now this is the measurements from ice. So now we're going back in time beyond 1960, all the way to the early 1700s with these measurements here. And what now we can see is that 100 ppm rise I was talking about before was preceded by a more gradual rise since the 1800s or so. And we have to go back to about 1750 before we kind of flatten out. And we call that the pre-industrial average, all right? And you can also see that the rise since about 1950 has been steeper than before. Does anyone know why it got really steep around 1950? Cars, yeah, it's the post-World War II industrial boom. So at that time when the world came out of a horrible war and there were a lot of cars being manufactured, but also huge industrial boom in the United States and Europe and the Soviet Union, a lot of CO2 was emitted at that time. And so you can actually see that in this history of the CO2 curve, which is pretty impressive. So, but I keep using this term industrial and pre-industrial and then post-industrial. And I want to explain actually how we know this, How do we know that this CO2 this rise that we have seen, that we have pretty clear evidence of happening, how do we know that it's us and not something else? You know, not some other source of CO2 like a volcano or something else, right? How do we know it's us? Okay, there's two, it's pretty simple. There's actually two things that we know. First, we actually know how much carbon we've been burning. So it's basically accounting. So what you can do is you can go back in history and put together the amount of gigatons of coal that have been burned, the amount of gigatons of oil that have been burned, and calculate the amount of CO2 that you expect to produce and compare that with what is in the atmosphere. That CO2 has to go somewhere, and it basically goes into the atmosphere and the ocean and a little bit into plants on land. And so when you do that accounting, the books balance. All right, the amount we put in is what we see. So there's that. It's very simple. And the second way is actually through chemistry. So it turns out that CO2 that comes from the burning of coal and oil, or what we call fossil fuels, has a very unique fingerprint. It doesn't look like CO2 that comes from volcanoes. It doesn't look like CO2 from really anything else. It's got this very unique fingerprint of old, dead trees, dead stuff, okay? Because that's what fossil fuels are, quite literally. These are old trees that decayed and formed this carbon-rich stuff that we're using now as an energy source, and they formed hundreds of millions of years ago. And now we're bringing it back up and burning it. And so as we burn more CO2, we actually see a change in the chemical signature of the CO2 in the atmosphere. And that's what I'm showing you here. So we're seeing the CO2 curve again now. Just like I showed you before, now it's going back a little farther in time. The ice cores keep going, as we'll see in a second. And that's in red. And then in black line, that chemical fingerprint of fossil fuels, which basically looks the same, okay? It's just paralleling the rise in CO2. And that's how we know for sure that that CO2 rise is coming from fossil fuels. So accounting and chemistry, it's us, right? All right, so why should we care? All right. So is this a problem? We have some CO2. What's the big deal? It's in parts per million. That's not a very high concentration. Maybe it doesn't matter. All right. So why is this a problem? Well, we have known for a very, very, very long time, okay, that CO2 is a great heater-upper. All right. It's a great insulator. And this actually traces back to the work of Joseph Fourier. So Joseph Fourier was actually a French mathematician and physicist. He's famous for his contributions to essentially signal processing. So for those of you who have worked in engineering, you may have heard of the term Fourier transform, which is basically taking a signal and partitioning it into different sine waves. That all started with Joe Fourier here. So, and why that's important for the rest of us who aren't engineers, well, our cell phones, everything that we talk to each other, all of that, you got to thank Joe right here, okay? So it goes back to Joe. So in addition to being interested in signals and how we actually process different energy signals here and there, he was interested in heat, which is also a kind of radiation. It's a wave. And he was interested in how heat interacts with gases. And so he was actually the first to propose that there might be something called a greenhouse effect on planet Earth. And he came up with that really simply. He said, you know, given the distance of Earth from the sun, it should really be much colder than it is. But it's kind of toasty. It feels okay out. So something must be keeping the Earth warm to kind of make it a nice place to live. And a couple decades later, his idea was actually confirmed by John Tyndall. But it sort of started with him. And the connection to the signals is really important because if we think of energy as a wave, all right, it's the interaction between gas molecules and waves that is actually the key to understanding how the greenhouse effect works. So it turns out that gas molecules, different gases, so CO2 is a gas, methane is a gas, nitrous oxide, all these gases we talk about being in the atmosphere, oxygen, they like to vibrate in response to energy, but only at a particular frequency, okay? So they're like piano strings. You hit them, and they only make one sound. So they only like to vibrate at a certain frequency. It's special ringing frequency. So if we think about, again, the energy that's coming into the Earth's system, which is like a wave in a way, it turns out that CO2 vibrates very strongly in the infrared radiation. So infrared, as some of you may know, is not the kind of radiation we can see. So light is made of visible radiation. The infrared is a little longer wavelength than that. Some animals can see infrared. You can see infrared if you get a nifty cell phone camera like this, and you can go around and take pictures of your friends and your coffee cup, and it's glowing because heat is coming out of that coffee cup, right? So we're seeing the infrared radiation coming out, the heat, right? That's what we're seeing here. So CO2, this is its ringing frequency. It's actually in the infrared radiation. What happens when infrared radiation hits CO2 is it vibrates, it moves like this, it moves like this, and it actually does cartwheels, which I'm not going to do because I'm not good at that, but it spins. And as it does that, it's absorbing the energy, okay? It's taking the energy from the infrared radiation and keeping it to itself to do its little dance. So that means the energy is absorbed. All right, so let's come back. How does this relate to actually how the greenhouse effect works? So 99% of the energy we receive is from the sun. Okay, there's really, geothermal energy is less than 0.1% of the energy reaching the Earth's surface. It's basically from the sun, comes into the Earth. Some of it is reflected by the Earth, by snow and ice, for example, which is very bright and reflective, by bright white clouds. Of the stuff that comes in, it gets absorbed by the planet and it's turned into heat. That's infrared. Heat and infrared, same thing. So the heat is now radiating out from the Earth. And if we didn't have an atmosphere, it would just keep going. It would just radiate back out to space. And Earth would be a very uninhabitable place. But we do have an atmosphere and it has greenhouse gases. And so like I was just talking about, when the infrared radiation is coming out of the Earth, it gets trapped by CO2 and other greenhouse gases, methane, nitrous oxide, that all do their dance, vibrate, and absorb infrared radiation. So this is our heat trapping blanket. And it's actually a good thing that we have some, because if we didn't have any greenhouse gases, Earth would be a very, very chilly, minus 18 degrees Celsius, or basically that's 0 Fahrenheit. So it would be frozen, the entire place. Obviously it's not, and we have greenhouse gases to thank for that. However, there can be too much of a good thing. And I'll give you a very extreme example. So let's compare Earth with a neighbor. So first, just to recap on Earth. So we've got our incoming radiation from the sun. Some is reflected off of the stuff that makes it. We have, in pre-industrial times, we had a 0.02% of our atmosphere was made of CO2. Now it's 0.04, right? So we're at 400 ppm. That's the same as 0.04%. So that CO2 is trapping that heat. And the net effect of that is actually about 33 degrees. So as I said, if without the greenhouse gases, planet Earth would have an average temperature of 0 Fahrenheit. With the greenhouse gases, it's actually 60 Fahrenheit or 15 C. So you see there's quite a bit of warming that's being done by that tiny bit of CO2, right? The 0.04%. And other greenhouse gases, but this is the main one, so we're focusing on CO2. All right, so let's compare that now to our neighbor, Venus. All right, so Venus is closer to the sun, so it gets a lot more solar radiation, but it's actually got such a thick atmosphere that most of that is reflected back into space. So ironically, even though Venus is closer to the sun, less actually gets through. But then its atmosphere is 96% CO2. It's almost entirely made of CO2. And the net greenhouse warming effect here is 285 degrees Celsius. So compare that with the 33 net effect on Earth. That's a lot of warming, which makes the surface of Venus a sweltering, very toasty, 460 degrees Celsius or 860 degrees Fahrenheit, right? It's crazy, right? So this is like what we call a runaway greenhouse. It's just too much, okay? So if you're thinking, okay, now I'm scared because I don't want Earth to go to runaway greenhouse, don't worry. All right, we're not close to Venus, and we probably won't get there. Nonetheless, that 100 ppm that we've put in since 1960, and the 50% increase that we've seen since the pre-industrial baseline is enough to start warming the Earth, because what this example is designed to give you a sense of is the power of CO2, all right? And how effective it is at trapping heat, very effective. So with that 50% increase, we've already seen climate change start to happen. So we see it in temperature, all right? So we have thermometers, so we can obviously know how global temperature has changed in the 20th century, and this is what it's looked like. So I'm showing 2016 and 2017 there. Very warm years. 2016 is the hottest year ever, okay, in the instrumental period at least, right? As far as we were keeping records. And the total warming is about, you know, since 1880, we're looking at a little bit about 2 degrees Fahrenheit globally. Tucson, also warming. Okay, the records at Tucson from the airport only go back to about 1950, but we see that Tucson is warmed by about 4 degrees Fahrenheit according to the airport. So a little bit more than the global average in Tucson here. And everywhere you go, you can actually pull out weather data and pretty much find that it's been warming almost everywhere on the planet in the 20th century. And what this has done is it's caused change to happen that we can see. It may not be so obvious sometimes sitting in the desert, but if you lived in Alaska, you would really know that this is real. So here's a photo of a glacier, Carroll Glacier in 1906, an old photo. Same spot in 2004, and you can see that the glacier is basically gone. It's retreated way up the valley, and where there used to be a proglacial lake, now it's just dust. Or another example, let's go to a tropical place, Miami Beach. This is a normal high tide at Miami Beach. It's what they call nuisance flooding. And what nuisance flooding is, it's just the fact that sea level is creeping up ever so slightly in Miami and globally, to the point where when you have a strong high tide, the streets are flooded, which is a huge pain. And they're talking about raising their streets and making huge infrastructure changes to address this issue in Miami Beach. So they're already feeling sea level rise. Or California, which, as I'm sure you know, just experienced the worst drought possibly in the last 1,000 years. And we know this drought was so bad in part because it's so hot. So droughts have 2 pieces. They have little rain and they have heat, which evaporates water and takes it away. And both of those things came together in 2015 to create this huge drought in California, which, as sure many of you know, is very disruptive. So the point is these things are happening and it's real. This is climate change and it's happening now. So where are we headed then? What does the future look like under a higher CO2 world? What should we expect? What should we expect in terms of temperatures or extreme events? This is the $1 million question, and it's the major challenge of the 21st century to resolve. What are we going to expect and what are we going to do? But you know, I would argue that, you know, how do we learn about how the climate system behaves in these higher CO2 environments? Well, you can look at the observations we have from the 20th century, the historical record. But in my opinion, trying to understand climate change by just looking at a few decades, it's like trying to understand a game by just watching a few plays. All right, you're only seeing part of the action. You don't know the rules. To get the rules, we need geology, right? We need the record of the past. We need to know how the Earth's climate has changed under dramatically different conditions, which have happened in geologic time. And so we can study them and learn from them, and then we know the rules of the game. So what I do at the University of Arizona is I do this, and I use things that we call paleoclimate archives. So we're talking about climate change. Paleoclimate is the study of climate in the past, right? So paleoclimate. And to do that, we need to tap into natural archives that record changes through time. So I already talked about the ice cores and how valuable they are for giving us those CO2 records from the bubbles that are in the ice. But there's other examples, tree rings, of course. And University of Arizona is actually famous for its tree ring scientists. We have the oldest tree ring science lab in the world. We also look at corals in the ocean, which accumulate layer by layer. So they're also a nice archive. Cave stalagmites. And finally, sediment cores, which I'll talk a bit about today, because that's the archive that I use most. So first, just another comment on the ice cores. So these things are collected with huge amounts of effort. I don't do this myself because I don't like cold weather, so I don't like to do this kind of field work. But I really respect the climate scientists who are out there in the middle of nowhere in very inhospitable conditions collecting these ice cores. Because there really isn't a better archive for CO2 change in the recent past. And so I just showed you that we were able to use ice cores overlapping with the Hawaiian record to look at CO2 from the pre-industrial to the present. But the ice cores go way farther back. And in fact, we can take the ice cores back 800,000 years into the past. So almost 1 million years ago, we can actually measure those bubbles in the ice and precisely know what CO2 and methane, methane being another greenhouse gas, that's CH4 right here, were like in the past. And what you can see is these jumps going up and down and up and down, and these are the ice ages. And then this, right? So that's us. So there is no analog for that as long as the ice cores have been around. So the geologist in me says, all right then, how far back do we need to go into geologic time to find the last time that we hit that 400 ppm bar, which we hit last year? How far back do we have to go? Any guesses? 3 billion? What else? Jurassic time. That's a good guess. Anyone else? 300 million? Okay, so these are all like, so Jurassic time, that's a good intuition because the dinosaurs, when the dinosaurs were around, it was very warm indeed, and actually there was very high CO2. Turns out we don't have to go back quite so far. We actually only have to go back 2 million years. But to get there, we have to switch archives. So the ice cores, this is as old of ice as we have. So we got to move to the sediment cores. And the sediment cores are really cool. We get them from a big ship like this one. This is the research vessel JOIDES Resolution. It is run by the United States, but it's funded by an international consortium called the Integrated Ocean Drilling Program. And what this is this is an open sea worthy ship. Goes all over the world with a giant, what looks like an oil rig on it. And it's a modified oil rig, and its purpose, of course, is not to drill for oil, but to drill for mud, which is what we really want as climate scientists. So it has a hole in the middle of the ship called the moon pool. And there's a giant piston core that comes down and gets sent down thousands of kilometers to the bottom of the ocean, stuck into the mud, pull it back up and bring it on deck. And then we have all this beautiful deep ocean mud, which may not seem like much to you, but there's a lot of climate information in these things as it so happens. So what the scientists do, we split them open, we take little samples out of them, and we're looking to measure things that tell us about the climate and environment of the past. And there's a lot that's actually in that seemingly boring looking mud. You can look for little microfossils, things that lived in the ocean and of course have since died. The coccolithophoras are these beautiful shells here. Foraminifera, we'll talk about those in a second. Dinoflagellates, or if you're near the coast, you can even get pollen from land that blew in and settled down into the mud. You might also measure physical properties, the size of the grains, to tell you about how the depositional environment has changed. Or you may measure different chemical properties, both things like different isotopes or molecular fossils, fossils that you don't see, but they still leave a chemical residue in the core, so you can put together what was living and what the environment was like. I want to talk about just one of these indicators today because there's so much and we don't have time to cover all of them, and that is actually these guys right here, the Foraminifera. This is what they look like when they're alive. So this guy is about the size of a grain of sand, and when it's alive it has these beautiful appendages that are reaching out, and it's a predator. So it's doing that to grab little brine shrimp to eat. Foraminifera is actually a protist. It's a single-celled organism that is inside a calcium carbonate shell, which is this part right here. And when it dies, of course, we lose all these beautiful spines. They're very fragile, so we don't usually find those in the mud. We're just left with the calcium carbonate shells, which look like this. And they come in all sorts of different shapes and sizes depending on the species that you're looking at. Again, these are the size of little grains of sand. So you could see them with your eye, but we mostly look at them under a microscope to see these beautiful patterns. So you can find these in the mud, sieve them out and study them. In addition to telling you the different kinds of species that were living, actually the chemistry in those calcium carbonate shells, these calcite shells, is the key to reconstructing past climate change. Believe it or not, we can do a lot by measuring the chemistry of these shells. So one thing we can do is we can actually measure in the calcium carbonate chemistry a particular type of isotope that tells us, believe it or not, what CO2 was. And the reason for that, I won't explain because it gets a little complicated, but the short reason is that actually when there's more CO2 in the atmosphere, there's more in the ocean, and it ultimately affects the chemical composition of these shells. So there's a relationship between the atmosphere and the ocean, and we'll actually get to that in a couple of slides. So for now, without going into the detailed chemistry, you have to trust me that we can do this. And this is how we get back to the last time it was 400 ppm, is with the chemistry of those little tiny shells. So the red part here is the ice core again. Here's 400 ppm. Here's the age. And the last time that we hit that was around 2.5 million years ago. Last time that we hit that consistently was more like 3 million years ago. And all these little dots are different data points from shells taken from different sediment cores collected from the deep sea. So we have to go all the way back to the Pliocene epoch, which is not as far back as some of you guys were saying. We have to go back to the Pliocene to hit the last time it was 400 ppm. So let's consider then, what was the Pliocene like? Okay, this is like the last time that we hit CO2, so maybe if we look at it, we might learn something informative. So the Pliocene looked like this. It was a warmer world, not extreme, but definitely warmer. So if you lived in the mid-latitudes in the Pliocene, it would probably be about 4 degrees Fahrenheit on average warmer. Doesn't sound like a lot, but if you lived in Tucson, it would be pretty toasty. If you didn't have air conditioning, you probably wouldn't live here, for example. The high Arctic was 15 degrees Fahrenheit warmer, so it was substantially warmer, okay? So it would have been really toasty if you were living in Alaska, a really different type of climate. And in fact, we can use geologic evidence, moraines, and also measurements of sea level at the Pliocene to reconstruct the Greenland ice sheet. And it turns out that the Greenland ice sheet was almost not there. So today we have a Greenland ice sheet. Okay, it's melting, but it's still there. It's pretty hefty. All right, several kilometers tall. In the Pliocene, it retreated except to the very middle part where there was still some accumulation. And so all of this ice was gone. It melted into the ocean. And that would have resulted in a sea level rise of somewhere between 3 and 5 meters globally, which is a lot. So you multiply that by, so we're talking about 10 feet, 15 feet sea level rise. That's pretty big. Now we're talking about something that's pretty big change. So you can imagine if you were living in coastal areas that the shoreline would not be where it is today. But in fact, we weren't alive in the Pliocene, as you know. In fact, we hadn't evolved yet in the Pliocene. Our ancestors had. Lucy, the Australopithecus afarensis lucy, famous fossil found in Africa, dates to 2 million years ago. So Australopithecus is one of the early splits off from the great apes that sort of went on to evolve into Homo sapiens, our species. And this is just starting to happen in the Pliocene. So Lucy was an upright walker, one of the earliest ones that roamed the savanna. But Lucy was adapted to the Pliocene climate. And it's important to remember that we are not. Now you might think, well, I live in Arizona, I'm a sun worshiper. But let me tell you, we are an ice age species, deep down. We evolved in the Pleistocene at the peak of the ice ages, when there was a lot of snow and ice around. And even though we evolved in Africa, we quickly spread to colonize even very, very, very cold areas very successfully. So we were never really meant to be a Pliocene species. We're an Ice Age species. It's an interesting perspective. Okay, so what if I want to go back further? What if we go back further? Someone mentioned the Jurassic. Let's not go quite to the Jurassic, but let's go back further into the Cenozoic era. So we're not going into the age of the dinosaurs. We're staying post-dinosaur extinction. But what we can do is we still have those marine sediment cores. We still have those little foraminifera guys. And scientists have literally measured thousands of these guys in the last 30 years and put together this master curve. So all that up and down you see in the black, those are individual data points that somebody or somebody's grad student, more likely, measured. This is an enormous amount of work. And with this community effort, we now have a temperature history of the world that goes back 65 million years. Pretty cool, right? So on the bottom, I'm showing you the epochs. In geologic time, we have all these names. So this whole thing is the Cenozoic, but these are the different epochs. We talked about the Pliocene, and there's some other ones here. Don't worry too much about remembering them, though. I want you to focus on this curve. So up is warmer here, and I converted the data into Fahrenheit. So these are actually measured on the foraminifera that live at the bottom of the ocean. So what these temperatures are is they're the minimum temperature on Earth, the coldest it could have been. Very bottom of the ocean. Today, the ocean's very cold. Okay, it's colder in central Canada, but the coldest it could be in the water is the bottom of the ocean. And so when we go back in time, so here's the Pliocene we're just talking about. It doesn't look too bad in this perspective, right? Because look at what happened before. So we go back here into the Miocene, pretty toasty, basically nothing freezing in the ocean. We go back before, and here, this big jump here, so that's when the Antarctic ice sheet first shows up. And again, we have geologic evidence for that. So we have good constraints. Causes a big jump in temperatures to cooling at this boundary. Before this boundary, there is no Antarctic ice sheet, or not a lot at least. So we're talking about here in the Eocene and the Paleocene is a truly warm world where minimum temperatures on Earth were like 45 degrees Fahrenheit. Minimum. So you can think what the maximum were. We'll have a look at that in a second. And it turns out, something amazing was that, again, we can go back to the chemistry in those shells, those little tiny shells, and we can also put together the history of CO2 over this time period. And this is an ongoing effort. We don't have as many decades of data, but here's what it looks like so far. And look at that. So, of course, not every bump matches up, but the trend is pretty clear. So when it's warmer back here in the Eocene 50 million years ago, CO2 levels, we think, were 1400 ppm, which is pretty warm. So the dotted line here is showing you the 400 ppm boundary, where we are today. So here we have the Pliocene, the last time we hit it. But when we really want to go way above it, we got to go back at least 30 million years. And we want to go into the more extreme world, talking about 50 million years. So really high CO2 now in this part in Earth history. And we have a name for times like this. We call them greenhouse climates, right? Because that's basically what's going on. We have high CO2 and it's hot. So what's cool about these greenhouse climates, they're extreme, all right? But we can learn some important stuff from studying them because now we're talking about really warm time. So what are these greenhouse climates like? I'll try and paint a picture of what they were like. So first of all, they had some weird stuff living there. So probably the most famous greenhouse climate thing is the Titanoboa. That's what you're seeing here. So this Titanoboa is basically a giant boa constrictor that was found, these fossils were found in the Amazon. And so here's your normal boa constrictor vertebra, and here's your Titanoboa one. So this thing is absolutely enormous. Big old giant snake. Okay, so why is that important? Well, snakes are ectotherms, which is a fancy word for saying cold-blooded. they can't regulate their body temperature, right? That's why they go hang out in the pass in the morning and they warm up and then they go away later. If you see them out here in the desert, they're trying to regulate their body temperature. So the idea is if you have these giant snakes, you really actually need a warm climate so that they're comfortable, because they would not do well in cold climates whatsoever. So the giant snake is sort of considered this kind of, you know, charismatic evidence for how warm it was in the last greenhouse climate, the Eocene, the Paleocene, and the Eocene. And so this is what actually the world looked like during this Eocene time, that peak greenhouse interval, 56 to 34 million years ago. All right, so CO2 was near 1,000 ppm. There was no polar ice sheets anymore. Greenland is gone, Antarctica is gone, which means 125 meters of sea level rise. So you can see that actually it flooded into the Amazon basin, and here in Florida's underwater and the Yucatan's underwater. And of course the continents don't look exactly like they do today. We're still building mountains over in India at this time. We're building mountains in the Andes, but it still looks kind of like today in terms of where the continents are. And no, and Antarctica hasn't moved. It just doesn't have ice in the Eocene. So this is kind of like an artist's rendition of what the Arctic might have looked like in the Eocene. And it looks like the tropics, right? There's a crocodile. There's some sort of monkey, tapirs. Crocodiles in the Arctic, really? Really? So we actually have fossils of crocodiles in the Arctic. So another one of those sort of faunal indicators. So crocodiles, like snakes, they can't control their body temperature. So they have ranges that they like to live in. Here's an example. So the preferred range is the black bar. And sorry, this is in Celsius, okay? But that's like 90 degrees Fahrenheit. And they can do a little bit more. But, you know, if you hit them with freezing temperatures like an alligator, it's not going to be happy, right? It won't survive. So that means that the poles weren't freezing, very minimum. And they were probably pretty toasty beyond that, to have this sort of environment that looks like the tropics at the high Arctic. It's really hard to imagine, but that's what the data say. If we go to the Antarctic, we actually have pollen and these things called phytoliths, which I like to think of as plant bones. They're little silica things that plants make, so plant bones, that tell us that palm trees and baobab trees were growing on Antarctica. I am not kidding. So, and there's a lot of these. It's not just like one. You know, they found a lot. Again, they're looking at the mud. This isn't all that mud that they're pulling up with that big ship. Baobabs, by the way, they're a tree that lives in Africa and in the tropics. So like palms, you know, they wouldn't be growing on Antarctica today, suffice to say. We can do better. We can actually give you numbers. And so some of my research is focused on actually getting some numbers beyond the crocodiles. Let's put some numbers on it. How hot was it, right? All right, so here's what we have. So we're actually looking at ocean temperatures now. So we've got the modern on the bottom. And it's just by latitude. So we have the tropics are, you know, your toasty 80-degree water. High latitudes are basically at the freezing point of seawater. And then we did a reconstruction during the Eocene using molecular fossils that are sensitive to temperature. And we are finding tropical temperatures that are around 90 degrees Fahrenheit. So we're talking about, it's close to your hot tub, right? It's getting there. Goes into hot tub in the uncertainties. And that pole temperatures are actually only 68 degrees. So huge difference in the poles. Slight warming in the tropics, but big warming in the poles. And so that means that the gradient between the temperatures was actually much lower than today. So today, the tropics to the poles is 30 C, but the gradient, the pole to equator temperature gradient is about half that, basically, is what we're saying for the Eocene. So it was a steamy time, right? 1,000 ppm CO2. All right, something else that's sort of interesting about the Eocene time, and that's that even though it was this what we call equable climate, we use equable because the poles and the equator were closer. Everything was kind of warmer, but it wasn't stable. There were some surprises. And the surprise shows up in our record of ocean temperatures. If you zoom in on this curve, it looks like noise, but if you zoom in, this little spike right here, there's actually multiple points here recording this sudden warming. Actually, it's a warming at around 55 million years ago. And we have a very unflattering name for that. It's called the Paleocene-Eocene thermal maximum. So that's a very scientific thing, but PETM for short. This little spike was discovered about 15 years ago. So let me walk you through what happened in this little spike. So what happened in this spike? So we've been spending some time putting together, figuring out what happened, and this is kind of the story. There was a huge burp of CO2 from somewhere. We'll talk about where in a second. Global temperature spike. I actually just showed you that here. That's the spike. This is the spike just smooth so you can see it easier. So this is minimum temperatures on Earth. Remember, it's bottom of the ocean, okay? So 75 degrees in the bottom of the ocean. You can imagine how hot it was at the surface. Toasty. CO2, we think, spiked from a baseline of 1,000 up to almost 2,000 temporarily. And we also have evidence of massive ocean acidification all over the world at this time. Let me show you what that looks like. You can see it. That's what's amazing. So this is a deep sea sediment core taken from the South Atlantic. And what happens? Here's a story of the event right before your eyes. So before the PETM, we have these sediments that are they're nice and white. They're kind of a dirty white. And that's all the forams. That's all those lovely little shells that are made of calcium carbonate, of calcite. And then the PETM hits. Boom. That's that boundary right there. Really sharp, really fast. The ocean acidifies, and we know that because suddenly all that white stuff in the core is gone. It's gone. And it's not just this core. We have 10 cores. You see this red layer everywhere. Everything's dissolved. So the ocean acidified. All right? So all you're seeing that's left is this red clay. And even 10,000s of years later, it's still there. So it takes a while for the ocean to recover, and then about 100,000 years later, finally, the calcium carbonate comes back. So what that means is that finally, the ocean recovered, and the acidification was over. So we have a big pulse of CO2. We have warming. We have ocean acidification. Where did the CO2 come from? Actually, there's been quite a bit of debate about that. There's basically 3 ideas. And I would say the newest idea is that maybe all of them are involved. The first idea was so-called methane clathrates, which are called fire ice. And that's actually normal ice, but inside of it is methane. And it forms on the slopes underneath below the surface of the ocean in sediments. When you bring it up, it'll release methane into the air. So the idea is that suddenly a bunch of these methane clathrates just got unstable because of an initial warming and released a bunch of methane. Methane will turn into CO2 in about 12 years, so it eventually becomes CO2 to cause the global warming. But some other people think that there is some volcanism, and there is the emplacement of, there is some evidence of volcanoes going off at the time. And even others think that maybe permafrost. So permafrost looks like this big wedge of ice underneath peat. And it's kind of like the clathrate, and that ice is trapping a bunch of methane inside. So if it melts, it can release a lot of it to the atmosphere. So there's still like a vigorous debate about where the CO2 came from. But the bottom line is that it came out, and it came out fast. And it basically messed up the whole world for about, 100,000 years or so. So a pretty extreme event, right? And here's the scary thing. That happened much slower than we're doing today. So even though when we look at that sediment core, it's a sharp boundary, right? It still took 20,000 years to cover that boundary. So for geologists, that's like, but for us, that's slow. And this is the rate that we're warming right now. If we continue our high emission rates with up to 25 gigatons of carbon a year, we are going way faster than the PETM, which is definitely scary, or it certainly scares me. So what are some of the lessons that we can learn from this event, from this warm world? So we went back to the Eocene. We saw everything was warm. There was no ice. There was this crazy warming event, which had ocean acidification, disturbed the ecosystem in the ocean. That event is probably the closest analog we do have for global warming, even though what we're doing is faster than today. But rather than looking at what happened in the past and trembling in fear of the future, I would argue that it kind of boils down to this. It's real. It's happening. Global warming is happening. It's us. I just showed you how we know that. It's bad for most people. Some people might enjoy the warmer weather. Maybe if you live in, I don't know, Saskatchewan. But most of us will see a bad side, whether that be sea level or droughts or hurricanes or something. And some people will win out and some people will lose out. But there's hope. It's not over. The story's not over. We don't have to be the Eocene, all right? We don't have to be like the Eocene. We have a choice. We have a choice because where we end up depends on how much we emit. It's very simple. And so this is a graph from the IPCC report. And it's just showing some future scenarios of like how much carbon we emit. And in the numbers here, that's the ppm of CO2. So we're already at 400, right? So if we kind of hang out where we are now, and maybe we emit a little bit more, but we hang in the 400s or 500s, I call that the Pliocene option, all right? So we're going back to a warm world, but it's not super crazy, you know? Although we still expect some sea level rise for sure. Now, if we go out here, this is the high emission scenario, and the so-called baselines are actually doing nothing, okay, absolutely doing nothing. Even this one has some remediation, some mitigation of CO2 emissions. This is do nothing. Now that I call the Eocene situation, right? That would send us into 1,000 ppm, which is where we were 50 million years ago, right? So, and these choices are important because they're totally different trajectories. So if we can hang out in the Pliocene, we can stabilize our warming maybe a little bit higher than we have today, but we can stop-ish, all right? We still have sea level in the pipeline. Remember, the Greenland ice sheet was still gone in the Pliocene, so we won't live to see that kind of thing, but future generations might. However, if we keep emitting, then we're going to go into the Eocene situation. We're really starting to lose a lot of ice and warm the world, and maybe increase the possibility of these crazy abrupt events, which we don't want to get into. It matters for ocean acidity too. So I just gave you this example of an ancient ocean acidification event, right, from the PETM. And just like the PETM, if we simulate future emission scenarios, if we stick with the Pliocene situation, that's a dotted lines, we can actually stabilize the pH of the ocean around 8, which is good. Okay, that means that the corals can eke by, maybe. We still will lose some, but not everything. But if we go with the Eocene situation, then we're talking about massive acidification that's on the scale of PETM. And in this case, this happens very quickly, all right, even in the future scenarios. So we can get to a pretty low pH of 7.5 by the end of the century if we keep emitting. So this is something that we will see. We will see. Or at least I'll see, maybe my kids will see. So there's choices. I think that's the key. There's choices, and the geologic record makes it clear what the difference between those two choices is, right? So I like this quote from Sherwood Rowland, he actually won the Nobel Prize in Chemistry for his work on the ozone hole. And he discovered that chlorofluorocarbons were destroying the ozone and started off the chain of events that helped us stop depleting the ozone layer. And he said, well, what's the use of having developed a science well enough to make predictions if in the end, all we're willing to do is stand around and wait for them to come true? All right? So this is really the situation I feel like we're in right now as when it comes to climate change. You know, we have predictions and we have the lessons of the geologic past. So we just need to decide what we're going to do about it. All right, so with that, I will say thanks, and I'd be happy to take some questions.
So as I mentioned before, before we take questions, I just want to announce next month's talk, and we'll return to the Thursday, January 11th at 6:30 p.m. And Jake Wade will be talking about the Anthropocene, the human footprint, which Jessica's done a great job with the prelude for that. So just by show of hands, Samantha's on one side, we'll just kind of alternate back and forth as we get questions. And again, pose your question and then pass the microphone back to us.
One thing that's been proposed is placing a fee on carbon. Can you speak to that?
Sure. So I'll start by saying that I am not an economist. I am a climate scientist. So, in terms of making decisions about how we respond economically to climate change, I would not call myself an expert in that realm. But I do think more generally that providing economics incentives to switch or at least diversify our energy source is a good idea. And so whether that means taxing carbon or establishing stricter emission protocols, or maybe encouraging R&D in solar or other energy sources that are more carbon neutral, I think all of that stuff is on the table as a way for us to create an economic incentive to switch over, because as long as fossil fuels are the cheapest, that's what people are going to burn.
So great talk. The carbon that's in the atmosphere right now is going to stay there a very long time, right?
Yeah.
So anything we add just increases the amount of CO2 and makes things worse, right? So it's not an easy solution.
No. People have talked about carbon capture and storage. Okay, so that would be a technology where we would, in theory, well, most of it's like you have a fossil fuel plant, but you capture the CO2 and then you bury it in the ocean or the land. There are no technologies currently that would actually suck existing CO2 out. And carbon capture and storage is still in its proto phase right now, so it hasn't been scaled up. So it's definitely a tough problem. But like I said, I think there's still choices that we can make that mean the difference between a moderately warmer world and like a really, really warmer world. And I guess my point is those are actually pretty different situations to get into.
So what you've described today has shown that there's a lot of work is going into determining how CO2 quickly got into the atmosphere, even way back in these old areas. Have you done any work to find out how the CO2 got out of the atmosphere very quickly in some of those periods?
Great question. So I didn't have time to talk about how the Earth actually recovered from the PETM, which we saw that it did, right? So we have studied that, and actually what happens on those, it's still a geologic timescale type process. So we're talking about 100,000 years. What actually happens is that rocks on land interact with CO2. They react with CO2 very, very slowly and absorb it. And it ends up being translated from CO2 gas into a dissolved form that's no longer potent. And then it gets sent out to the sea and buried again in those calcium carbonate sediments. So on very long time scales, the Earth can handle it. And it does it by actually reacting silica rocks on land very slowly with CO2. And CO2 is an acid, so it actually very slowly will etch away at the rocks. So on 100,000 years, the Earth can buffer CO2, and that's actually beautifully shown in the PETM, where you have that slow recovery and the bright white sediments come back. The bright white is the CO2. It's just been transformed into calcium carbonate and buried again as rocks. And it's no longer in the atmosphere. And that's what will happen in the future as well. The problem is the time scale of that is still very slow compared to a human time scale.
The humans all exhale CO2, and there's been a dramatic increase in the world population and also the number of mammals and domestic animals in the world. How does this factor in, or does it factor into the increase in CO2?
Yeah, so population change feeds into CO2 increase, but not directly as in exhaled CO2. So that's actually still a relatively small amount. It feeds in regards to energy use. So it's just that more people are burning more fossil fuels, are burning basically waste, in poorer parts of the world, which is very CO2 rich. So it's more people burning more things. It's not more people exhaling. So the exhaling itself is still a pretty small part compared to the amount of carbon that you put out when you actually just burn stuff. And that makes sense, right? Because when you burn stuff, it gets pretty hot. It's a lot of energy released. When I exhale, it's not that big of a difference, right? So a lot more carbon, a lot more energy.
How soon will I have to move from Saddlebrook, and where do I go?
From where? Sorry, say that again.
How soon do I have
Saddlebrook.
to move from Saddlebrook?
I don't know. Well, you know, okay, so the challenge we're facing here is going to be drought, right? It's about water. And I haven't had a chance to talk about water in the Southwest, but what we know and what we don't know. So we know that it's very likely that it will get overall drier in the Southwest, and that actually you could predict from temperature alone. So that whole idea I mentioned with California, the warmer it is, the more water is evaporated, the drier it is, even with the same amount of rain. That's true in arid places like here. So, so most of the predictions for the Southwest are a very dry future. And there's also predictions for reduction in winter rainfall. The predictions regarding the monsoon are less certain. So there are some camps that think the monsoon will get much weaker. There are some camps that think that it will shift in terms of its timing. And there's a third camp that thinks that it might get stronger. So the science on the monsoon is not settled. And that's because it's a very difficult system to predict with climate models. So it's actually, that's one of the focus of my research groups is studying the past changes in the monsoon. And we're using marine sediment cores from the Gulf of California to actually reconstruct how the monsoon has changed in these past warm worlds with exactly that question, trying to answer what happens when there's higher CO2. Is the monsoon stronger or weaker? Maybe the geology can help us figure it out. Yeah.
There's a group that meets at Mountain View monthly. It's called Citizens Climate Lobby that can explain the fee and dividend program. And if you want to find out how that works, just Google Citizens Climate Lobby.
Okay.
So are we in what you would consider somewhat of a natural cycle? And if that's the case, are we forcing this to go faster by all of our carbon emissions?
So before we started emitting in the geologic time frame, we're in this kind of rhythm of the ice ages, where every 100,000 years we had an ice age. And if we hadn't emit CO2, we would very slowly be cooling, the globe would very slowly be cooling, heading back to the ice age, not within our lifetimes, obviously, but now that we've emitted and we're over 400 ppm, remember that the Pliocene didn't have almost no Greenland ice sheet left, and actually we've eliminated the possibility of ice ages now for the near geologic future. So in the very long geologic future, the Earth may again assume a sort of cryosphere-rich stage, but we don't recover from the CO2 very quickly. So we've knocked ourselves out of the ice ages, and by ice ages I mean the times when there were large ice sheets on North America. So the Laurentide ice sheet, for example, that was here 20,000 years ago. We're not going to see that again for a very long time. We weren't in any other kind of natural cycle, really. Solar forcing has declined since 1950, so we know that the sun hasn't contributed to the warming. Volcanoes actually cool the climate, so it's certainly not volcanoes. Basically, since 1950, the climate forcing has been CO2 from human emissions. And before that, CO2 mattered, but natural forcings were also involved. But since 1950, it's us. It's just us.
Translating your research into a current economic and political situation, should the United States get back into the worldwide reduction program? Should we be mining more coal than we are now? What should we be doing today, if anything, to reverse the temperature increase?
So there's 4 ways to adapt to climate change, 4 responses. 1, do nothing. It's a choice we can make. 2, adapt, move. All right, just get up and move. If you don't like the climate where you're at, move to a place where it's not so bad. 3, mitigation, and that's anything that reduces CO2 in the atmosphere. So that would be, committing to the Paris Agreement, diversifying fuel sources so that there's less CO2 emissions. So definitely coal is the most CO2 rich. So the more coal you burn, the more CO2 will be. If you can get coal reined in, then that would be a good thing. So mitigation is anything that you can do to kind of reduce emissions by switching up the energy source. And then the 4th option is something we call geoengineering. And that's actually like the carbon capture and storage thing I was talking about. Things like putting mirrors in space, injecting aerosols into the stratosphere. These are kind of like pie in the sky things. And many of them are very risky because they involve modifying the Earth's radiation. And there might be consequences that we don't fully understand. So whole-scale geoengineering, or some people call it climate hacking, is considered to be pretty dangerous, but people are researching it anyway, and I think that people are trying all these things, but definitely the easiest way to, be safer and the most straightforward way and economically feasible way as well is just mitigation. So again, diversifying your energy source, maybe with some technologies that help really, maybe capture CO2 to some level. And that would be the fastest and quickest way to lower CO2 would be something like that. So a strong investment in alternative energies, and maybe carbon capture is scaled up. But that would require, the latter would require serious economic investment to do. Yeah.
Occasionally, cows will come into the picture as creating a huge amount of methane per surface area and mass. Is this reality, something to be concerned about?
Yeah, the cows are like, they're like a quarter or third of the methane emissions, so they're no joke. No, there's a lot of cows. There's a lot of agriculture, raising cows for food, but also just cows, and not just cows, but any other animal that also basically produces methane in its digestive tract. But cows are the most common one. So regarding the cows, I mean, methane is a problem. Obviously, it's a greenhouse gas in of itself. It oxidizes, turns into CO2 very quickly in the atmosphere, about 12 years lifespan. And that's because it's a reduced gas. It's formed in the cow's stomach in a place where there's no oxygen. So once it sees oxygen, it's not stable. So it turns into CO2. But I would say that the cows, if you add up the methane and the CO2, the cows are actually a small part of the total emission. So still the focus has mainly been on mitigating the fossil fuels and not so much on the cows. But I think less cows, yeah, why not,
There obviously are others out there who don't agree with your conclusions, and I'm wondering from sort of a science standpoint, those on the other side, where would they attack your scientific facts or conclusions that you've gone through with us tonight?
Yeah, well, I think you can go to some dark places on the internet and get some ideas about that, but they might not agree, but right, science is science. Like, these are the facts, I mean, you can choose to ignore it if you want. That's the do nothing option. And if people don't think it's right, then, they can think that, but that's an opinion and that's not science. So, 97% of scientists agree that global warming is caused by humans. Science is pretty simple. I hope I demonstrated that tonight, right? CO2 from us, it warms the planet. End of story, right? It's hard to pick that apart. Now, I think people can disagree about what to do, because that's a political decision. And that's a discussion that we all have to have, because everyone has different priorities, and that's a real discussion to have. But, you know, the science is done. At this point, this is really about politics and economics and everything else. And so, you know, I don't see any credible, I guess, scientific disagreement with the kind of stuff I've shown you today. There's no one really who disagrees with it except for crazy people on the internet. So you can believe them.
So we.
And that, yeah, that's true. Yeah.
I'd like to thank everyone for their amazing interest. Jessica will be after for just a little bit if we have a few questions, but we'll want her to get back home before it gets too late. And I'd also just remind everyone to please, if you'd like, fill out the evaluation forms. We definitely incorporate that. And I have one question, Jessica, if you wouldn't mind. Oftentimes, geosciences is a male-dominated field. I'm curious about how you got your start in it, what motivated you, and what you hope to do in your career.
Sure. I was motivated to study, in particularly Earth history, because I loved history of people. But then I realized I could study Earth history, which was even cooler, because I thought these ancient events, like some of the stuff I talked about today, were just unbelievable, and I wanted to understand how we knew that and how I could help understand what these things, what had happened. And that kind of just evolved over time. And so, you know, I got my undergrad degree in geology, but like I said, with a lot of liberal arts classes. So history, normal history is all a big part of my education. And and then after that, I worked as a technician for a while, and I realized that I really wanted to do this and do my own science. And so, so then I decided to go to grad school, and the rest is history. And now I'm really motivated to basically by questions like, for example, yeah, how will the monsoon change in the future? You know, like I said, well, maybe we can use geology to answer that. That's usually my response. But it's big questions like that that I really want to understand with my research. And we use a lot of chemistry, actually, on the ground, a lot of chemistry and geology together to get there. So I showed you the results, but there's so much effort that's going behind every data point. It's amazing. You'd be blown away. And I think U of A is a great place to be because we have a long history of doing climate research, especially issues regarding water and drought in the Southwest, and some great interdisciplinary resources, great people to work with to kind of focus on these problems. And we also have top-notch facilities in geoscience to be able to make all those fancy chemical measurements I was talking about, which is really important. So, I don't know if that answers your question.
That's a great answer to your question.
Yeah. And I'll just say that if you want to know more about geosciences, there is a couple of very short pamphlets outside that just tells you about us and our students. And it's a great department, really great people, and amazing scientists that have ended up here at the U of A because we just love living here and working here, you know, and working at the U of A. So,
thank you again. We look forward to seeing everyone in January and have a wonderful holiday season. Good night.